Okay, so the problem here is, to fill in all these numbers here. Let's see, 310 divided by D, and that's going to give you 1.542. I hope you got these numbers. 1936 divided by this number D, 2. Again, try to put this number in your memory or someplace, store it on your calculator, and you can just do 1936 divided by that number, and that would be 9.630. Um, this will be 840 divided by D, that's 4.178. If you didn't get these numbers, again, check your division. This divided by this number 201.0345 is going to give you 13,649. All right, the sum of all of these numbers will be 29. This is totally expected because that's the number of seats. We use this number to find D, so that's not a surprise that you get D. Okay, but the problem, of course, is that all of these are fractions. Well, not fractions, but they're decimal numbers. And so how do you find the minimum quotas? Basically, it is the number prior to or to the left of the decimal point, right? So 1, 9, 4, 13. These are the minimum number of people, representatives, these states should get, right? Because, I mean, after all, you have at least one person here, at least 9, and 4, and 13, and so on. If you add up these numbers, what did you get? I think you get 27, okay? So what does it tell us? We need 2 more. Remember, now we have 29 seats, right? So we can give 2 seats, okay? In other words, 2 of these states will get an additional seat to the number of people representing their states. All right, so let's compare the remainders. The remainders, it's pretty easy. All you have to do is to write down the portion of the standard quota to the right of the decimal point, right? 542,630.178.649. All right, you don't have to worry about adding these numbers because that would be meaningless. The seats, which ones are the biggest? Now, remember, I can pick 2 largest remainders. In this case, ooh, that's a close race, isn't it? 0.649, this is the largest one. Okay, this is the largest. Let me go ahead and write this. And the second largest is this one. All right, so it looks like D, second largest. D gets the first, and then B gets the second seat, and that's it. So, so instead of 9, we'll get 10 here. And instead of 13, we have 14 here. The other states do not get any, right? So this is 1 and this is 4, right? Hopefully you have understood what's happening here. Hamilton's method allows this kind of calculation and allows a pretty simple method of choosing the number of seats, okay? Now, what I want you to pay close attention to here, now stop what you're doing and pay really close attention to this, okay? Because I'm going to illustrate one of the problems that suddenly appeared, and in fact, people, as mathematical as people were, as smart and intelligent as founding fathers were, they did not see this coming. And this actually took place right after the Civil War. Again, going back to a little history lesson, in 1880, okay, this kind of thing really happened. They increased the total number of seats in our Congress. And guess what happened? Remember when they used to have 28 seats? Watch this. When they used to have 28 seats in this 4-state country, A had 2 seats, B had 9 seats, C had 4 seats, and the D has 13 seats. What about this? When you add 1 extra seat to the Congress, entire national government, the legislative body, 2, 9, 4, 13 became 1, 10, 4, 14. So there was an increase of 1 in B and 1 in D, right? So 10 became, so 9 became 10, 13 became 14. State C had 4 seats. State C still has 4 seats, did not change. But guess what? State A, even though the total number of seats increased in Congress, State A actually went from 2 to 1. They lost a seat. Why? The numbers didn't change. These populations didn't change. They lost a seat precisely because the total number of seats increased. Does it sound paradoxical? Yeah, it is paradoxical. That's why people didn't see it coming. Mathematically, this is proved to have to be able to occur. In other words, this is a possibility, and it's always been a possibility. It just didn't happen until 1880. So people were pretty shocked about this. All right. So this is called a paradox. Okay. The paradox here is that an additional number of seats, a total number of seats, could possibly allow certain states to lose a representative. Okay, and this really happened to the state called A. What is that state A? In 1880, right after the Civil War ended, we have a southern state whose name starts with an A that actually lost a seat because the number of representatives in Congress increased. Right, and that state is Alabama. And as a result, this is the famous Alabama paradox. The Alabama paradox is a paradox in which a state loses a seat because and when the total number of seats in Congress or in the council or assembly increases. It is hard to imagine that this could actually happen, but it does, and it did in 1880 under Hamilton's method. All right, so this actually pinpointed a problem with Hamilton's method. Hamilton's method wasn't as clever or good as it possibly could be, okay? Because, I mean, certainly an increase in the total number of seats should not cause a state to lose a seat, right? Everybody should get at least the same number of seats as before, if not more. Okay, so again, going back to a little piece of history, Hamilton had a very politically powerful enemy. Okay, in fact, he probably had more than that, more than a few. Hamilton was a gentleman, but he had a few people who didn't like him. Notably, well, okay, so you guys probably have memorized the lyrics. And when I started to teach this, there was no musical called Alexander Hamilton or Hamilton. But everybody knows now, I think, that Hamilton's chief enemy was the third president of the United States of Virginia. What was his name? Thomas Jefferson. Okay, so Jefferson really didn't like anything associated with Hamilton, like Hamilton's method. Okay, so let me just tell you what happened. And then some of the historical lessons, some of the things that really happened in history, I will explain in another part of this video, namely when we go over the first half of the worksheet for this lesson. Okay, so to make a long story short, Jefferson came up with his own method. Okay, so Jefferson presented his own method, came up with this method called Jefferson's method. All right. Now, meanwhile, Hamilton had many friends in Congress and in other places. So this method was presented to the then the legislative bodies, and then they both passed, right? So in both chambers, it was passed, and it was presented to, what happens, by the way, when a bill, which sort of establishes Hamilton's method as the official method for apportionment, okay? Like any other bill, when the bill is passed by both legislative chambers, it goes to the president's desk, okay? Now, the president at this point was the first president of the United States. Thomas Jefferson was his name, not Thomas Jefferson, George Washington. George Washington was also a Virginian, just like Thomas Jefferson. They were good friends. Remember, Jefferson did not care for Hamilton. So when this method, Hamilton's method, was presented to George Washington, instead of signing this, he talked to Jefferson, a fellow Virginian, and Jefferson says, "Oh no, you don't want that." Okay, and the thing is, Jefferson was smart enough. Remember, by the way, he had been an ambassador to France. Okay, and he was very well educated, especially in science and mathematics. In fact, he devoured the Euclid's Elements, and you know he became an architect. He was the person who founded the University of Virginia. If you go to his house in Monticello, the Monticello in Charlottesville, Virginia, you can still see his house with all kinds of geometric wonders. And so he was quite a competent person. He was smart enough to realize that Hamilton's method had this one property, which was, and as you saw this earlier, okay, in Hamilton's method, you saw state A win the extra seat, right? And the reason was because Hamilton's method actually favors smaller states. Did you get that? Yes, Hamilton's method generally favors smaller states. Now, Virginia was not a small state. Jefferson wanted a system or method in which larger states will be more advantageous, okay? So clearly he didn't like Hamilton's method. So he went to his fellow Virginian, George Washington, the president, and said, hey, Mr. President, I don't like Hamilton's method. The Congress likes that, so they passed it. But there's one way not to allow that to become the official method of apportionment, and that is called the presidential veto. Right? Now, there was no veto up until that point. So basically, George Washington, as the president of the United States, decided to listen to his friend Jefferson and decided to veto this bill. This became the very first veto in the history of this country. The first veto was Jefferson telling George Washington to veto Hamilton's method. All right, and so that's exactly what happened. And instead, people wanted to use, or he wanted to use, Jefferson's method, which favors, yes, larger state like Virginia. Okay, so you can see Jefferson saying, hey, George, let's make Virginia great again. And that's exactly what happened. So Hamilton's method was turned down and something else was used. Actually, Jefferson's method didn't win either. Okay, it turned out another method called Webster's method won the vote. But let me talk about Jefferson's method here. Okay, and we will not do any others because I think two methods is plenty for us to understand the intricacy of this apportionment problem. All right, so Hamilton's method used the remainder to figure out which state should get that extra seat. All right, so let's see how the Virginians, try to make America great again. How did they do that? Well, this time, what Jefferson decided to do was to, it was something very different, okay? In fact, we had the quota, right? The standard divisor D. He decided to change that, to modify it so that you don't have to worry about the remainder. Let me explain what happens here. In Jefferson's method, you round down each quota, okay? But you don't look at the remainders. If more states, if more seats are available, then you start messing with that number D. Reduce the standard divisor, okay, to make it into a modified divisor until the total number is obtained using that minimum quota. All right, so again, let me explain just a little more. These are the same numbers as before. Okay, the total number of people in this country, the 4-state country, is 5,830. The quota, this is the standard quota. All right, and so these are 1.489. These are the same numbers as before, 9.298, 4.043. I mean, same as before, like the very first time we did this. And then, of course, this adds up to 28, not surprisingly, okay? The minimum quota, remember, you throw away the this first part, and so it's, I mean, the last part after the decimal point. So it's 1, 9, 4, 13. This is as before. This adds up to 27. That was the problem, right? We need one more seat to be filled. Who is going to get this? Okay. Now, instead of looking at the remainder, listen really carefully here. This is the difference between Jefferson and Hamilton. Jefferson basically came up with something that was at least had to be different from Hamilton's method, and it had to be reasonable. So his idea was, well, the reason this adds up to 27 is because we divided all of these numbers by the standard divisor D. So if we make that D smaller, these numbers will increase, and eventually one of these minimum quota numbers will get to the next whole number, or the quotas, standard quotas will become the next larger integer. All right, so instead of, let's see, D was 208.21, whatever, right? So how about if you use 200, let's say 200. How about 199? How about 198? 190, 6. No, let's use 195. All right, now why do we choose this? Because I just happen to know 196 is still too large, but if you go to 195, it actually works, okay? And so this number will be given to you on your homework or on your test or whatever. Let's say if you use 195 as your new modified divisor, then what's going to happen to this? All right, you see what we're doing here? Again, all you have to do at this point is to divide this number by this number, okay? And let's see what happens in this new system. I'm going to use blue to denote the new numbers. 310 divided by 195 is 1.590. 1936 divided by 195 is 9.928. 840 divided by 194 is 4.308. 2,744 divided by 194 is 14.072. Okay, notice these numbers are kind of similar to these, but they're all slightly bigger. Because we are dividing by smaller numbers, the results, the smaller number, 195, then the quotient, the answer of the division problem would be slightly bigger, okay? How much bigger did it get? Well, 1.4 became 1.5. But still, the minimum, okay, if you round off or if you get rid of the point, the portion after the decimal point, it'll still be 1. This is 9. This is 4. But oh, look at what happened to D. 13 point something became 14 point something, right? So you take this number. All right, so it looks like 19413 became 19414. The extra seat was awarded to state D with the largest population, like Virginia, surprise, surprise, okay? And this now adds up to 28. So you can see that nothing changed except the last one, okay? D obtained that extra seat. And by the way, remember, if you used Hamilton's method, state A had 2 seats, but state A lost a seat. Okay, so this is compared to Hamilton's. See, Hamilton wanted to favor a smaller state. He was from New Jersey, New York, and Virginia was the bigger state back then. Virginia, under Jefferson's method, would obtain an extra one. Okay, because that's how Jefferson imagined the bigger states should have more. I mean, bigger states already have more representatives, but he wanted to use a method that is even more advantageous to larger states. Politics, right? Yeah. All right, let me just finish this up with a couple of more comments here. Webster's method is another one. Now, we used to teach this. We no longer cover this because, as I said before, Hamilton's and Jefferson's method would take enough time to understand and to do problems on. But Webster, that is Daniel Webster, the one that's famous for the dictionary, is also come up with his own methods in which you don't always round down, but you can round up or down each quota, this is supposed to be quota, to decide, right? So if it's like 1.99, he would round it up to 2. Okay. If more seats are available, use Jefferson's method. Even inside of Webster's method, which means you use the modified divisors. If the total number of seats exceeds the seat available, then you increase the standard divisor and so on. This is called Webster's method. You don't have to know this, but remember there is a method called Webster's method. And then there are several other methods are introduced, never really used, okay? And then remember 1880, in 1880, after the census of 1880, the Alabama paradox surfaced to everybody's surprise. And so this clearly was not desirable. It violated what we call a fairness criterion. A fairness criterion is a statement that is considered, fair in any kind of apportionment. And there are several fairness criteria. Experts have identified a few other criteria. So we have like a set of 4 or 5, what is known as fairness criteria, all right? And a good method of apportionment should satisfy all of the fairness criteria because after all, we want a fair system, right? Okay, so the question now is which method avoids all of these undesirable results. In other words, which method would avoid and would be guaranteed to avoid all unfair situations and therefore guaranteed to satisfy all fairness criteria? Well, the answer, you have to wait until fairly recently, 1983. Okay. Belinsky and Yang are the two economists, political scientists, who were studying this very problem. And they looked at this method, Webster's method, Hamilton's method, which was already a problem because it creates the Alabama paradox, Jefferson's method, and everything else. And guess what? These two mathematically proved that there is, and this is unfortunate, but they actually proved this. Amazing. There is no fair apportion method. This is doomsday prophecy. There is no fair apportionment method. Basically, anything that anybody can come up with is going to violate one of the fairness criteria. Okay, so no matter how good an apportionment method is, there is some sort of unfairness associated with it. Okay, and this was actually proved in 1983. So that is a pretty powerful, maybe surprising result. Okay, so this was the first lesson from chapter 8, and this dealt with apportionment. And I think we all should be aware of these efforts to make things fair. We should always be aware. We should also be aware that it has been proved that there is no such thing as a completely guaranteed to be fair method of apportionment. All right. Historical struggles are real. Okay, so there was all kinds of a bunch of things were happening between Jefferson and Hamilton, and this is just a part of history. But there was, just mathematics were involved. Mathematical problems were also involved in these struggles and in politics. All right. So next time we'll talk about the theory of voting, which is another big topic in terms of how mathematics is related to politics. Until then, I hope you have a great week, and I'll talk to you later. Bye.